Alright, hello class, and today we're going to be looking at some lines which I like to call direct variation lines because they're all lines that pass through the origin. And so usually we can characterize lines by the equations of the lines, and in this case the equation of the line would be y is equal to the slope of the line times x. But what if I don't want to characterize it by the equations, or what if I don't want to characterize it by the slopes? Is there another way I can characterize these lines? And there is, using another feature that these lines are characteristics that these lines have. And the feature that we're going to have is not just including the slopes. We're actually going to be using the feature of what happens when a line intersects the x-axis. And when a line intersects the x-axis, then we can see that you can have what's called a type of angle that occurs where the intersection of the two lines are. And that angle is what we're going to be looking at to characterize the lines. So here, for example, if I just take a look at just this line right here, and as you can see here, it intersects the x-axis, but there's an angle formed between the two. So as I move the line, as you can see, the angle is changing. And so if I take a look at this actual angle, it has an angle measurement, and as I move the angle, as I move the line, the angle measurements change based off the degree of rotation from the x-axis. Well, let's create something that involves this angle as well as these lines and the x-axis. And what we're going to do is we're going to create a triangle. But before we create the triangle, we want to kind of scale everything. So we're talking about, let's start with the unit circle. And we call this the unit circle because the radius of the unit circle is 1. So any point on the unit circle is the distance from that point in the origin, which is the center of the circle, is going to be 1. So here we have a unit circle. And if you notice, each of the direct variation lines will actually intersect the unit circle at a point, okay? And so just to make it a little bit simpler, we're just going to focus on the green line, and we're going to see where the green line intersects the unit circle. And actually it intersects it in two places here, and it actually intersects it over here, but we're going to just focus on this point just for right now. So now that I know that I have an intersection point between my green line, direct variation line, and the circle, I'm going to draw a triangle. And the triangle is going to have the same angle that we talked about, but it's also going to have a right angle. And if I take a look at the actual coordinates of the triangle, which involves the lengths, I can see that there's a relationship between the lengths of the sides, the length of the legs of the right triangle, and the coordinates of the right triangle. And as we can see here, the length and the leg are the same, and the hypotenuse is 1. So as I change the line, the coordinates of the legs change length because their legs are changing length, but the hypotenuse stays the exact same. And so we're going to focus on those type of angles. So is there a relationship between this angle and the coordinates of this intersection point, which we know there's a relationship between the coordinates of the intersection point and the lengths of the legs of the right triangle? Well, there is, and if you remember from geometry, there's these things called trigonometric ratios. And the most popular trigonometric ratios are sine, cosine, and tangent. And the definition of sine, cosine, and tangent are trig ratios, such that sine of an angle is the ratio of the opposite leg length divided by the hypotenuse. Cosine trig ratio is the ratio of the adjacent leg length divided by the hypotenuse length. And tangent ratio is the ratio of the opposite leg length divided by the adjacent leg length. But since we know that we're in a unit circle and this right triangle has a hypotenuse that has length 1, then we're going to modify these ratio definitions just slightly, because we already know that in our case we have a unit circle. So that means that for sine and cosine, we have our side lengths being equal to either sine or cosine, as we can see here. So if we want to relate the angle of rotation with the coordinates where the line intersects a unit circle, we can use sine, cosine, and tangent. So we're going to develop I call it a trig chart with some very popular angle measurements. Of course, the domain of the angle measurements are from 0 to any infinity, so we don't really have time to list all of those, but we can look at some very popular ones. So let's take a look. So here I have two very popular right triangles, the 30, 60, 90 right triangle and the 45, 45, 90 right triangle. And just like the right triangles in our unit circle, we know that the hypotenuse is 1. So if the hypotenuse is 1, then here are the side lengths for these measurements. So if I want to figure out the sine of angle 30, remember the sine is opposite over hypotenuse, so the sine of angle 30 would be 1/2 over 1. And so here I've developed a chart to represent that for the sine of 30. And as you can see here, the sine of 30 is 1/2. The cosine would be the adjacent over the hypotenuse. So the adjacent is square root of 3 over 2. And since the hypotenuse is 1, then our cosine is square root of 3 over 2. And vice versa. And our tangent is the opposite over the adjacent, and it basically is 1/2 over square root of 3 over 2, and it ends up simplifying to square root of 3 over 3. Over here for the 45, 45, 90 triangle, the legs are the same length and the hypotenuse is 1, so the cosine is the square root of 2 over 2, and the sine is also square root of 2 over 2. And the tangent, which is opposite over adjacent, is basically just 1. All right, and so I put these ratios up here just so that we can remember. And we do the same thing for the 60-degree angle. Now in this case, in this picture, the 60-degree angle, I would basically have to rotate it and flip it some so that you can see the same orientation that was on the picture, but for some reason I'm having trouble with that. But you guys get the picture. So going from the 60-degree angle, we can see the opposite side leg is square root of 3 over 2. That's why the sine for 60 degrees is square root of 3 over 2. The adjacent leg is 1/2. That's why the adjacent leg is 1/2. Cosine of the angle is 1/2, and vice versa. Well, that at least talks about the 4 lines in the 3 lines in the first quadrant. But what about the 3 lines in the other quadrant? Let's take a look and see what happens to the coordinates as we change the line. And just to refresh your memory, the x-coordinate represents the cosine of the angle, and the y-coordinate represents the sine of the angle. Okay, and so as we change this, and again, I really rounded the coordinates to the 10th place, so that's why it may look a little bit off, but it's actually rounded to the 10th place. All right, so as we can see, as we're changing our angle of rotation, you see the coordinates are changing. But what happens when we leave the first quadrant? The triangle now leaves the first quadrant into the second quadrant. What do you notice is different about the signs? Well, the cosine now is negative and the sine is positive. And as we continue moving our triangle around, in the third quadrant, now both sine and cosine are negative, as you can see in the coordinates. And that's because the x is at a negative on the negative side and the y is on the negative side of the axis. And then we get to the third quadrant, cosine is positive and sine is negative, because in the, sorry, did I say third? In the fourth quadrant, cosine, or the x value, is positive and the y value is negative. So I have a lovely little chart that helps us refresh our memory about this relationship, and to see why in that case, then that means that our cosine and sine values are going to have different signs in the different quadrants. So let's take a look at the second quadrant. Here is our table for the second quadrant. 120, 135, and 150 degree angle creates the right triangle of 30, 60, 30, 45, 60s over there. And as we can see, the cosine is only negative in the second quadrant, so therefore the tangent is negative, but the sine is positive. And as we move to the third quadrant, you can see that now the cosines are negative. The sines are negative and the cosines are negative, but the tangents are positive because of that relationship. And as we move to the fourth quadrant, we see that the sine is negative and the cosine is positive, therefore the tangents are negative. All right, and that concludes our video. These notes will be available at the link.